let's talk about seeing the unseeable. I mean, what would it actually be like to peer into the atomic world and see the literal building blocks of reality? Well, today, we're diving into an incredible technology that puts that power right inside your web browser. So here's the plan. First, we'll tackle the huge challenge of seeing the unseen. Then, we'll discover this amazing microscope on the web. After that, we'll get into the science behind it, the electron's secret phase, and how we go from phase to picture. And finally, we'll jump in and start exploring these digital nanoworlds. All right, first up, the absolutely massive challenge of actually seeing something as small as an atom. I mean, think about it. How do you actually see an individual atom? It seems impossible, right? To even try, scientists had to invent one of the most incredible tools ever made, the electron microscope. And that brings us to the core problem. On one hand, you have the transmission electron microscope, the TEM. It's a modern marvel, powerful enough to image single atoms. But here's the catch. That power is locked away. These machines cost millions of dollars, they need a team of experts to run them, and getting time on one is incredibly difficult and expensive. So, what's the workaround? How do you get that kind of power into the hands of, well, everyone? What if you could take a multi-million-dollar microscope and put it on a laptop? Well, this is it. An absolutely ingenious solution. Researchers created a fully functional, real-time electron microscope simulator that runs right in your browser. No lab, no multi-million-dollar price tag. You just open a tab and you're in. And you know, this is about so much more than just making a cheap version of a microscope. It's about building intuition. The creators themselves said the goal was to give students a visceral feel for what's going on, to let them play and explore and really get it without needing a deep background and advanced math. So when you fire this thing up, you get this amazing 4-panel view. You've got your main image, which is that live atomic scale view. Then there's the diffraction pattern, which is like an X-ray of the crystal structure. The power spectrum maps out all the repeating patterns in the image, and the dark field is a super cool tool that lets you pick out and highlight just the things you want to see. Okay, so you're probably wondering, how on earth is this possible in a simple web browser? The secret isn't just clever coding. It's a really beautiful piece of quantum mechanics. It all comes down to one core concept, the de Broglie phase lag. Here's the key idea. As an electron, which behaves like a wave, passes through an atom, it gets a tiny nudge, a little shift. That tiny, almost unnoticeable shift is the phase lag. And it's the secret sauce that makes this whole thing work. Let's make that more real. Imagine that electron wave is a perfect ripple moving across a pond. In empty space, a vacuum, it's just a nice, even wave. But when it passes over an atom, the atom's electric field is like a little dip, a trough on the bottom of the pond. The wave dips into it, speeds up for a split second, and the wave crests get bunched up. That bunching up effect, that's our phase lag. And here's the really elegant part. The more stuff the electron passes through, like a heavier atom or a column of atoms, the deeper that trough is, and the more the wave bunches up. So there's a direct connection. We can't see the atom itself, but we can precisely measure the effect it has on the electron wave that passes through it. Okay, so we can measure this invisible phase lag, but that's just data, it's not a picture. So the next big question is, how do you turn this invisible map of phase shifts into an actual image we can look at? The answer is a brilliant optical trick called Scherzer defocus. It's a very specific focus setting in the microscope. By setting the focus just right, you can make the parts of the wave with the biggest phase lag, where the atoms are, appear dark, and the parts with no phase lag, the empty space, appear bright. Suddenly, the invisible becomes visible. The atoms just pop right out of the background. So, this clever method, calculating the image based on just one pass-through, a single slice, is what makes the whole thing run in real time. A full-blown simulation is way, way more complicated. So, just how much faster are we talking about here? Get this. It is 65,000 536 times faster. Let that number sink in for a second. That's not a typo. This one beautiful approximation makes the calculation nearly 66,000 times more efficient. And this chart puts that number into perspective. For every single image that appears instantly on your screen in the simulator, a full traditional simulation would take, well, 65,536 times longer. That is the breakthrough. That's what takes this technology out of a supercomputer lab and puts it right into a browser tab. So with this unbelievable power at our fingertips, what can we actually go and see? What kind of digital nanoworlds can we explore? Honestly, the possibilities are just staggering. You can explore the perfect, beautiful lattices of crystals. Then you can find the tiny flaws and defects that give a material its properties. You can zoom right in on the boundary where two completely different materials meet. And you can even look at single, complex molecules. Let's check out a concrete example from the research. What we're looking at here is a bicrystal of gold and zinc oxide. That means we're zoomed in on the exact atomic seam where these two totally different crystal structures are stitched together. And using that 4-panel display, we can really pull this structure apart. The main image, yeah, it shows the neat columns of atoms. But look at the diffraction pattern. It clearly shows two overlapping sets of dots. That's our two crystals. And then, using the dark field tool, you can actually select the pattern for just one of the crystals and instantly highlight only its atoms in the main image. It's just so powerful. But it gets even crazier. We can go from looking at metals and minerals to looking at the very molecules of life. For instance, here's a simulation of a single hemoglobin molecule. And this is where the simulator does something a real microscope struggles with. See, in a real TEM, the intense electron beam would start to damage a delicate biological molecule like this. But in the simulation, we can see it in its perfect, ideal state. As the researchers said, we can see what it should look like without all the damage you'd get in a real experiment. It's like seeing the perfect blueprint. So what this all means is that the nano world is no longer some far-off place, locked away in an expensive lab. It's here. It's accessible. It's for students, for teachers, for scientists, for anyone with a curious mind and an internet connection. It completely changes the game. So the real question isn't whether we can see the world of atoms anymore. The question is, now that it's just a click away for all of us, what are we going to discover next?